So we have classical physics telling us that light can behave as a wave. On the other hand, we have modern physics telling us that light can behave as a particle. It took a while, but physicists finally came to terms with the fact that light can behave as both. This phenomenon is known as the wave-particle duality. According to Maxwell's experiments, light is an electromagnetic wave that consists of alternating electric fields and magnetic fields. It is these electric and magnetic fields that store the energy that is being carried by the light. This wave nature of light is supported in the single-slit and the double-slit experiments. Light waves were shown to interfere with each other, and diffraction patterns could be observed. The only way to see these bands of constructive and destructive interference is to conclude that light does in fact behave as a wave. We also have evidence that light behaves as a particle. Photons are massless particles that carry energy in the amount given by Planck's constant times the frequency of the vibrations. The two big experiments that confirm this particle nature of light are the photoelectric effect and the Compton effect. It is not easy to visualize this duality. We often like to neatly categorize things and expect them to obey the rules that we set. This just isn't the case when it comes to light. But then it gets better. In 1923, Louis de Broglie extended the wave-particle duality to electrons. He argued that if light could behave like a wave and sometimes as a particle, then it must be true that particles of matter could also exhibit wave properties. He proposed that the wavelength of a matter particle would be related to its momentum, just like the wavelength of light was related to its momentum. We can calculate this wavelength for any piece of matter. For example, a 0.2 kilogram ball moving at 15 meters per second. We find the de Broglie wavelength to be 2.2 times 10 to the negative 34th meters, which is extremely small, imperceptibly small. This is going to be true for any regular-sized object, so the wave properties of ordinary objects go undetected. But if you look at an average electron, we see that the numbers come into line a little better. Since an electron has a really small mass and a high rate of speed, we end up with a wavelength on the magnitude of negative 10. Still pretty small, but big enough that we can show that electrons begin to show things like interference and diffraction patterns.